Standard cosmology treats the vacuum of space like an empty theater. Matter and energy are the actors, and space-time is the passive stage where the performance happens. Gerald Welch's unified space-time architecture inverts this relationship. In this framework, the vacuum is highly active. This representation shows the native continuum. UST defines the spaceline state through 4 specific descriptors. It is dark, cold, repulsive, and highly quantum. Under this model, spacetime is a dominant, active baseline that matter and energy actively suppress simply by existing. UST categorizes matter, energy concentrations, and bound systems as occupancy. As this diagram illustrates, introducing an occupant into the native continuum forces a reaction. The occupant radiates continuum suppression, damping the native dark, cold, and repulsive behaviors of the vacuum around it. We are evaluating version 1.0 of this architecture as a speculative structural blueprint rather than established physics. Before a theoretical framework can generate mathematical proofs or observational data, its internal logic and ontological boundaries must be rigorously constructed. That is what we are auditing today. This flowchart maps the foundational causal chain. Occupancy causes suppression, and suppression creates continuum departure. Continuum departure represents the overall magnitude by which a specific local region deviates from the unsuppressed native baseline. The Welch Continuum Index serves as the indexing framework itself, the conceptual coordinate space where local continuum states are locked. While WCI acts as the container, the actual state readings placed inside that container are expressed through the KGN profile. Decoupling the indexing framework from the readings themselves is an architectural necessity. It forces the framework to define the local state on its own merits, preventing standard observational biases from contaminating the logic. The KGN reading system uses 3 proposed independent axes for measuring departure: kinetics, gravity, and nature. A local reading might look like the vector plotted here: 12, 47, 9. Kinetics measures continuum excitation. It tracks the shift from an inert, cold native state up to a highly energetic radiant state. Gravity measures continuum organization. 0 represents native, release-dominant behavior, while 100 marks maximal confinement. At a reading of 50, we find the Minkowski Horizon. This is a dynamic balance between expansion and contraction, an equilibrium condition rather than a physical location. Nature measures realization, scaling from the native, probability-driven quantum state up into a hard, defined classical geometry. This leads to our first pressure test. We must ask if classical realization is truly an independent property, or if it is merely a downstream consequence of high gravity and high kinetics. Until mathematical derivation proves these 3 properties do not bleed into one another, the independence of the KGN axes remains a vulnerable working hypothesis. The UST model enforces a strict rule: curvature is not gravity. Standard models show mass directly warping a grid into curvature. In UST, gravity is an underlying organization state, while curvature is merely its spatial footprint. Gravity manifests in 2 ways. One footprint is spatial curvature. The other is its temporal counterpart, chronature. Because space and time are unified aspects of the same continuum, suppressing that continuum forces parallel changes in both spatial geometry and temporal behavior. For our second pressure test, chronature must produce novel predictions. If it only describes standard relativistic time dilation, the new terminology is redundant. It must predict dynamic shifts across the repulsive to attractive spectrum. Separating the underlying gravity state from its visible spatial and temporal footprints is the mechanism that allows UST to propose testable physical behaviors. Where does electromagnetism, the strong nuclear force, and the weak force fit in? UST rejects the idea that these gauge interactions are direct properties of the continuum itself. Instead, the current working hypothesis is that gauge interactions act as the energetic machinery that builds and binds occupants together. Under this model, standard forces do not define spacetime. They build the localized structures that suppress it. The largest current limitation of the UST framework is the absence of a mathematical formula to map these illustrative KGN scales to actual physical observables. This topological map highlights deep cosmic voids. These massive, empty regions provide the low occupancy, low suppression conditions required to test UST empirically. If the architecture is accurate, these voids should exhibit observable shifts back toward the native state, specifically showing high repulsive gravity and quantum dominance. A KGN reading in a void should bypass the Minkowski equilibrium entirely, dropping below 50 as it approaches a native baseline reading. Finding unique chronature or curvature signatures inside these voids that contradict standard models is the only path to validating the UST framework. The primary strength of UST is a decoupled ontology that forces a distinction between underlying continuum properties and observable manifestations. Its primary weakness remains its speculative nature, relying on illustrative scales rather than rigorous math. Theorists must now focus on mathematically proving KGN independence and mapping physical phenomena to the Welch Continuum Index. While unified space-time is not yet a proven theory, its rigid architectural blueprint provides the structured, falsifiable scaffolding needed to push cosmology beyond its current paradigms.